Good afternoon, dear students. Welcome to another session of Verilog HDL. So in previous session, we started off with the discussion related to data flow modeling. So in which we have discussed what is meant by continuous assignment, how it is achieved in Verilog HDL, then what are the different assignment which are present, that is implicit continuous assignment. Then apart from this, we discussed regarding delays. There are three types: regular assignment delay, implicit assignment delay, and net declaration delay. Then we came across with what is meant by expressions, what are operands, what is meant by the operators. So in expressions, it basically involves the operands and operators together in order to produce some result. So that is what we saw with few examples. Then operands are the different data types which are available. They can be any one of the data types which are available in Verilog HDL. So to name few, we have mentioned over here, that is constants, integers, real numbers, net data types, register data types, times, bit select. Then we have a part of those bits which we can select, then memories and function calls. So these are the different kinds of operands which we can work around. Now we discussed regarding a few of the operators. So what is the operator? Operator is intended to look out for what kind of operation has to be performed on the operand or operands. So that is what we discussed. So in this case, D1 and D2 are the operands, and double and percent is the logical ANDing of both. Here, exclamatory mark is a negation. It is performing negation of one bit. And here the operand is A of 0. So this is what we have, what is meant by operators. So we have different types of operators. We started off with the discussion with these things. So we discussed up to, say, arithmetic operators were discussed. And to remember, we should know that there are three types of operators, that is unary operator, binary operator, and ternary operator. Unary operator requires just one operand. Binary requires two operands. Ternary requires three operands. So here we saw the few of the binary operators which requires two operands, that is multiply, divide, add, subtract, and modulus, which fall under the arithmetic operators. Under this also we have two unary operators, that is minus and plus. That is unary operators minus and plus. So whenever we are using this over here, right? So be careful, because minus 7 mod 2 will provide a remainder of 1, but the sign will be related to the first element which is present over here. Similarly here, 7 mod minus 2. So remainder is 1, the sign will be related to this one. So it will be evaluated to plus 1. So this is one thing what you have to note down. So this specification like minus 4 and plus 5. So whenever you're using minus this thing, so always use or specify the operands in its say decimal or hexadecimal form, because if you just observe here, minus 10 divided by 2, it will be evaluating to minus 2. But the same thing if I specify it in this format, that is sign followed by in which base format it is, and then followed by the number. So here minus, it is decimal number, number is 10, decimal 10. So if I do it in this form, what happens is it might end up in unexpected results, because when we put in this form, right, it will be dealing in 2's complement. So you have to try to analyze the result in 2's complement form. So you're expecting that the answer is minus 2, but you might end up in different result, which is actually result of the 2's complement. Okay, so when you are dealing with the negative signs, so be careful. So okay, so that is one thing what you have to note down when you are using say the arithmetic operators. In that specifically the unary operator minus. Then we discussed regarding the logical operators. So we had some discussion regarding this logical operation. That is, the output of a logical operator related to the logical operator is a one bit value. It is either true or false. Another one special condition which comes is X, that is ambiguous value. So when does ambiguous value come in? Whenever in any of the operand there is a bit which is either X, bit or bits which is either X or Z. So if this thing comes in logical operators, you will be encountering the ambiguous value. Logically speaking, if you're using it in say some if statement or any other statement, it will be evaluated to false condition. Okay, so three this thing are possible over here. So here another thing is logical operators, they can take variables and expressions as the operands. So that is what we have seen over here. So one another thing to remember when you're using logical operations is this part, that is if the number is 0, it is equivalent to logical 0. If it is not equal to 0, then it is equivalent to logic 1. Okay, it is equivalent to logic 1. So therefore here if you just see, it is like logic 1 ended with logic 0 because a is 3. So logic 1 ended with logic 3, logic 0, 1 and 0 will evaluate to 0. Similarly, logic 1 ORed with logic 0, it will evaluate with 1. So it is just a 1 bit result for this for this logical operators. And another example wherein you have one term x. So if this is the case and if you're performing the logical operation, the expression evaluates to x. So this is what is happening. Now here this is an expression. A is equal to, you're checking whether A is equal to 2. So this is an expression. So you're using logical operation with respect to the expressions also. So this one either it should evaluate to true or it should evaluate to false. So that is what this ANDing operation is looking for. Okay. So then we came across relational operators, that is greater than, less than, greater than equal to, or less than equal to. So we had discussion regarding this. So one special thing what we have to do is what happens if a bit is x in the operand. So in that case, the expression evaluates to x. Otherwise, it will be based on the condition. It will be evaluating to either logic 0 or logic 1. So relational operators also lead to one bit operation. So only one bit result will be obtained. That is either true or false. Either A is here if I just take either A is greater than B, true, or it might be false. If there is any bit which is either Z or X, that is high impedance value or unknown value, then it evaluates to X. That is ambiguous value. Then we came across equality in which we had logical equality and logical inequality. Special thing was case inequality and case equality and case inequality. So in this one, you are just looking for zeros and ones. If x and z come in the bits, then the result will be the ambiguous value. So for example, here you have a is equal to, only two equal to's are there. So this is logical equality. If a and b are equal in terms of its zeros and ones, but if there are x or z values in a or b, then that expression evaluates to x, that is ambiguous value. Similarly, for a not equal to b also, it will be either true, false, or the ambiguous value. But whereas in case equality and case inequality, what happens is every bit by bit, even if it is 0, 1, x or z, will be compared. So here you can see that if a is equal to, that is 3 equal to's are used, we check is a equality is k equal to b in each of the case. So bit by bit, if I just check whether it is equal. So here only two possible values, true or false, that is 0 or 1. Similarly, for a not equal to b, using case inequality is again either true or false. It cannot be z or x. So it will be comparing each bit by bit. So we looked at that example. So these are simple. A and these are simple. One thing just to note down is this part. So here you are just checking. You can just check out these three. So here you are checking in case by case. So whether first bit is same, that is z and m, whether z and m are equal. So whether first bit is same, if it is 1, whether this is 1, if this is x, whether this is x, if this is x, whether next bit is also x here, if this is z, whether this is z. So each are compared. If this was 0, then it would be false. if this statement would be false. So the same thing is presented over here. So this one evaluates to logic 1. So here you can see Z, this evaluates to logic 0 because 1xx is same. 1xx is same, but the last value is x over here. So this creates the logical 0 output. So here also you are checking whether they are logically not equal. So if I just look at, so first three bits are same, but the last bit is not same. So therefore they are logically not equal in terms of case inequality. So we have discussed up to that point in the previous section. So now we'll be moving further. So next is bitwise operators. So the name itself tells that the operation has to be performed bit by bit on the two operands what you are using. So here you have negation and say broken pipe, then caret operator and caret operator with the negation or negation with the caret operator, which gives you the XNOR operation. Now let us see what are the possible things. What are the possible values of the operands and what is the possible output you will be getting. So the possible values of the operands are 0, it will be either logic 0, logic 1, or it will be an ambiguous value x value, or it will be a high impedance value. So here high impedance value Z is treated same as x. So in bitwise operators, Z is treated same as that of x. So it is treated as an ambiguous value. Now here negation is the only operand which uses only is the only operator which uses only one operand, whereas the others require two operands. Others require two operands. So let us see what the truth tables of these operators. So here first one is AND. So in AND operation, what is the condition? That if any one of the bit is 0 or any one of the input is 0, the output results in 0. So here we can see that 0, 0, the result is 0. So here this input is 0, therefore this also turns out to be 0. And here this part is 0, that is this operand is 0, therefore this result is also 0. And even if it is x, it is 0 over here and 0 over here. So when both are 1, then only the result will be 1. If both the bits are 1, then only the result will be 1. Now if it is logical 1 and if the other one is x, then the result is ambiguous value, that is x. And if both are ambiguous value, then the overall result is also ambiguous value. So just remember, if any one of the input is 0, the output is 0. If both have to be 1, then only the output will be 1. So apart from this, if it is x, then it will be evaluated to x except for this part. Okay, if any of the one input is 0, the output is 0. So that is whether it is whether the input in whether the other input is 0, 1, or x. If any one of the input is 0, the output is resulting in 0. So similarly, we have ORing operations. You can analyze it in the same way. So what does OR do? If any one of the input is 1, any one of the input is 1, then the output is 1. So in this case, say if this input is 1, no matter what these inputs are, the output is 1. Similarly, if this bit is 1, no matter what these bits are, the output is 1. And rest all conditions follows. If both are 0, output is 0. And if it is x, and if it is x, and this is 0 or this is x, it evaluates to the ambiguous value. So this is even z is treated as same. So this is also equal to, even if this value is z, it will be equivalent to x and the same result will be obtained. So similarly, XOR, you can just check out the operation, what is happening over here, even for XNOR. Let us come to negation. So in negation, if the bit is 0, it will be negated and the result will be 1. And if the bit is 1, it will be negated and the bit will be 0. But if the bit is ambiguous value, then the result also will be ambiguous. So this is what is happening in bitwise negation. So let us see the examples related to these. So here we have taken an example where X is a 4-bit binary number and these 4-bit values are 1010, and Y is also a 4-bit binary number, it is 1101. Similarly, Z we have 4-bit binary number which is 10 and 1 bit is X over here and the last one is 1. So what does negation do? Negation performs bitwise negation. It performs bitwise negation in this case. So here what happens is each bit is checked and it will be negated. So here we are negating X. So here what happens is the first bit is 1. So the result of the first bit will be 0. It will be negated. So this is 0. This will be negated and it will be made 1. Then this is 1. It will be negated and it will be made 0. And similarly it continues. So here you can see that this is 1010. But the negated version, that is the result is 0101. So it is performing bit by bit operation on this. Now similarly X and Y. Now there is one implication what you have to check out, that this and the logical and, there is slight difference between these two. Now here you can see that this is bitwise and which in which you have one single ampersand. So what this does is it takes X and Y, and bit by bit it performs the operation. So here the operation is ANDing. So operation is ANDing. So what happens in this case? So it is 1010 and the other number is 1101. So now you are ANDing these two. So 1 ANDed with 1 is what? 1. 0 ANDed with 1 is 0. 1 ANDed with 0 is 0. 0 ANDed with 0 is 0. So you are getting this result. So you will be getting this result. Now if you want to perform logical ANDing of these two, what happens is I have to check whether these numbers are non-zero or zero. So here you can see that this is 1010, which is actually not equal to, so this is a non-zero value. Similarly, this is also not equal to 0. So these two are non-zero values. So logically speaking, it is like this is logic 1 and this one is also logic 1. So if I perform 1010 logical ANDing 1101, so it is like this is a non-zero value, so it will be logical 1 ANDed with this is also logic. This is also treated as logical. This is non-zero, therefore this is also logical 1. So 1 ANDed with 1 is what? It is true. It is true. So you can see that logical ANDing results in 1 bit. The result is 1 bit. Whereas for the bitwise operation, it depends on the operands. How many bits are there? It depends on the operands. Okay. So logical ANDing results in 1 bit result, whereas this one it is equal to the number of bits which are present in the operands. In this case, bit by bit operation is performed, but in this case, depending on the operand whether it is non-zero or 0, the operation is performed. If the number is 0, it is treated as logic 0. If the number is non-zero, it is treated as logic 1, and then the operation is performed. So that is what is happening in this case. So here we had a logic operation, right? So here we can see. So it is A and B. This is logical ANDing. A is non-zero value, therefore it acts as a logical 1. B is a 0 value, it acts as a logical 0. So 1 ANDed with 0 is what? It is 0, that is false. So only 1 bit result is obtained. So it is logical 1 ANDed with logical 0. So this is what is happening. Okay. So this is the difference between your your bitwise operators and the logical operators. Logical operators. So this is performing ORing operation bit by bit. This is performing XORing operation bit by bit. Now one thing to note down here is, so here what you're doing, here you're doing XNOR operation between X and Y. The last one, if you just observe, X and Z. Now in Z, what has happened? So in Z, we can see that the third bit is X, whereas in this one, I don't have any X. So we'll do again bit by bit operation and see what is the, so 1 ANDed with 1 is what? The first bit, which is 1. 0 and with 0 is 0. But 1 and X will evaluate to what? Based on the truth table what we discussed. It will evaluate to X. And the last one, 0 and with the 1 is 0. So this is what is happening in this case. Okay. So this is these are few examples related to these things. Okay. And another one thing to note down is logical operators can have three possible values: 0, 1, or X. And they'll be performed based on the operands of this thing, whether they are non-zero or zero. But in bitwise operations, bit by bit evaluation is done. So they have given an example over here how these two are different. Okay. So next one we have reduction operators. So what happens in a reduction operator? So this is a say unary operator. It is a unary operator because it requires only one operand for its performance. So here we can see that it is AND, NAND, OR, NOR, XOR, XNOR. So these are few reduction operators. How they are utilized? How they are utilized? So here in previous also we had single AND, single OR. So here we have two operands. Here we have two operands. But in reduction operator, you'll be having only one operand. The operator will be operating only on one operand. So reduction operator is unary operator. Whereas the bitwise operator, except the negation, all are binary operators. That is, they require two operands for its performance. So how they are different now? So if we just look over here, so we have X, which is given by these values. That is, it is 1, 0, 1, 0. Now, if I want to reduce this one, what we do is if you specify it as ampersand X. So ampersand X, here ampersand is acting as a reduction operator. So what does it reduce? What is the result we get when we perform such operation? So here what we do is we perform bit by bit operation over here and see what is the overall result. So here what operation is required? ANDing operation is required, and it is a reduction and only one operand is there. So this is how I identify that this is a reduction operator. Ampersand is a reduction operator. It is not the bitwise operator. Here we can see that AND is present between these two. That is, it is operating on two operands. So this is bitwise operator. So which will be operating bit by bit on the value. So X and Y is there. X first bit of X will be say ANDed with first bit of Y. Second bit of X will be ANDed with second bit of Y and so on. But in this case, since only one operand is there, what happens is it will take each of the bits and it will AND the entire bits. So that is whatever reduction operator is there, that operation is performed with these bits. It will be performed with these bits. So here we can see that what's the first bit? It is 1. What's the second bit? 0. Third bit is 1 and last bit is 0. So and in between we have the reduction operator which is performing its result. So it is like 1 ANDed with 0, the result again ANDed with 1, the result ANDed with the next bit, that is 0. So if there are 10 bits, all the 10 bits will be ANDed and the overall result will be presented. So here you can see that if for AND operation and if any one of the bit is 0, the overall result is 0. Therefore, the result will be just a 1 bit. Result will be 1 bit and its value will be equivalent to the reduction operation performed with respect to the operand which is present over there. So here we are performing ANDing operation, that is a reduction operation using the AND operator. So here when all the bits are ANDed, the result is 0. So similarly you can see for OR this thing. So here you can see again this OR operator is using only one operand. So this is how I can make out that this is a reduction operator. So if I OR all the bits, the end result will be 1. End result will be 1. So for reduction operators, the end result will be 1 bit result. End result will be 1 bit result. And the bit by bit, this thing is performed from right to left. That is, you move from this direction to this direction. So here we have caret operator, which is performing the XORing operation. It's performing the XORing operation. So this is how the reduction operators will be used. Say you want to check the parity which is present in the bits, so you can perform these operations. So you want to check whether there are even number of ones or even number of zeros. You want to check that, so you can go for reduction operators directly instead of you counting the bits and keeping a track of based on a counter, incrementing if one is encountered and then seeing whether that counter is even or not, whether it is divisible by 2 or not. So instead of doing that, you can perform this operation directly. So reduction operators are useful in such cases. Okay, so next we have the shift operators. So we can have two kinds of shifts, that is the right shift and left shift. So these operators do the shifts based on how many bits you want to shift around. So whether you want to perform right shift or left shift by say n number of bits, so you'll be specifying that amount. Now here we can see that the operands have to be vectors and the number of bits to shift. So here we'll be having the operand and the number of shifts you want. So and this x or whatever operand is there, it should be a vector. This thing, since if you are shifting it, it should be a vector representation. The vacant bit positions here, what happens to these things? It is filled with zeros. It is filled with zeros, and you do not have any wraparound. Wraparound in the sense, suppose you have a number over here. Now if I'm shifting it, if this bit comes over here, then it is wrap around what is happening, wrap around which is happening, so that we are not doing over here. So if I shift it, what we do is, if I have some number like this, if I want to shift it, this bit won't come here, it will be lost forever. And when I shift this number, it will be like 0 1 1 1. And if I shift it in the other direction, it will be 1 1 1 0. So this is what is happening in these cases. And the 0 is filled in the vacant places, which is obtained due to the shifting operation. So here we have x is equal to 1 1 0 0. And in the first one, we are performing 1 bit shift. So when we perform 1 bit shift, what happens is this bit moves here, this bit moves here, this bit moves here, and this bit goes out, and one vacant place is created here. So it is like 1 1 0 is there, this 0 is out, one vacant place is present here. So this vacant place is filled with 0. So therefore you have 0 1 1 0. So 0 is filled in the MS bit position for say right shift. For left shift, what happens is it will be moving in the other direction. Moving in the other direction. If that is the case, now what happens in here? So this one moves here, this one goes out, so it gets kind of discarded. 1 0 moves here and 0 moves here. So there is a vacant place in the LSB part. So this part is filled with 0. So when you're performing left shift, 0 is filled in the LS bit position. So here you're performing two shifts which are required. So when we perform two shifts, what happens? So here, this bit moves once here and once here. So you'll be getting a bit over here. This bit moves once here and once here. So two shifts. So similarly, this bit moves once here and once here. So this goes out, and what is I did the other. So here it is actually a left shift. That is a left shift. So I have to move in this direction. So what happens is this bit has to move twice. So it is almost like discarded. This bit has to move out this side. So this is also discarded. This bit moves two positions towards this side. So the first bit becomes 0 and this one to the next to this thing. So there are two vacant places which are there. So these vacant places are filled with 0, 0. So this is what is happening in these cases. So why you require such kind of operations? You might have studied or gone through a few of the DSP equations which mentions shift and add, shift and save. So such kind of operations are required when you're performing say DSP kind of implementation. So DSP say convolution and other stuff. So you require these things. So for that purpose, you can go ahead with these shift operators. So next one is the concatenation operator. So concatenation, the name itself tells that I have to concatenate two, say, operands. I have to concatenate two operands, two or more than two. I have to concatenate two or more than two operands. Now here, one thing to remember is the operands have to be sized. You cannot go for unsized operands. You cannot concatenate those things. It is like you don't know the size of that operator and you want to concatenate. So this might end up in some erroneous results. So I should be knowing how many, say for example, how many bits are present and how many bits I'll be concatenating together. So if I concatenate one bit with another two bits, I'll be getting total three bits. But if I don't know the size, then it will be posing a problem. You might be running out of the memory, or when you're storing that number, you might be storing it in a location which provides less space as compared to the number of bits. For example, you are concatenating say 2 bits here and 3 bits here, but the memory can store say only 4 bits. So in that one bit again goes off. So again, if this number is increased, so it becomes a problem. So what is you should remember that unsized number in this size is not specified. So here you can see that A1. So 1 specifies that this is a 1-bit number, it is binary and the value is 1. If I don't specify this value, but I specify say the pick along with the specified say binary hexadecimal or any other this thing, those are termed as unsized numbers. So for example, so here we specified say 2 bits are there. I'll take binary and it is 0, 0. If the same thing, if I specify, if I don't put the number, if I specify just in this form, so this is sized number, this is unsized number. I haven't specified any size over here. Okay. So this is unsized number. So this is not permitted in a concatenation operator. Now let us see the syntax related to that. So first of all, the operands have to be sized. Next, if you have to concatenate, you will be using the comma separator. You will be using the comma separator. And what all operands you'll be able to concatenate. You will be able to concatenate say 1-bit value. You'll be able to concatenate more than 1-bit values. That is, your operands can be scalar types, scalar net data types, and registers, and vector net data types or registers. And even you can perform bit by bit bit level of concatenation. So only specified bit I want to concatenate, I can perform that, and only specified selected number of bits I want to concatenate, I can do those also. So in short, The data type can be a net data type or register data type. Under that, it can just be one bit or more than one bit. So it implies that it can be scalar or vector. And if it is a vector, so I can say concatenate the third bit of this one with the first bit of this one. So specific bits can be concatenated. Or else I want to concatenate this one bit with the only the first two bits. I don't want this one. So I can perform that also. That is what is part select implies. So even with the size constants also, you can go ahead with the concatenation. Okay, so let us see just few examples over here. We have A is, which is one bit in binary and its value is 1. B is 2 bits, it's binary, it is in binary form, it is 0 0. C is 2 bits, it is 1 0. D is 3 bits, it is 1 1 0. So all are in binary representation. Now I want to see how concatenation can be achieved. So concatenation operator involves the two braces and a comma. Two braces and a comma. So open brace, comma, and a close brace. So it depends on how many operands will be present in between. Those many commas will be put through. So here we have Y. So open brace, operand B, comma C, and a closed brace. So what is this specifying? You are concatenating B and C. So the result will be first the B bits, that is 0 0, and next the C bits. You are not specifying how many bits. So it will by default it will take all the bits, and these are sized numbers. So it will not pose any problem. So it is 0 0 and 1 0 is the result. And what is the size of this one? It is 4 bits. So here we can see that B and C are being concatenated and the size is 4 bit. Similarly, you can see that in this case A, B, C, D, and you have taken one additional this thing. You can perform it in this form also. It is not specified anywhere over here. So directly you can specify the bits over here. So you can see that A is 1 bit, B is 2 bit, C is 2 bit, D is 3 bit. So you can concatenate different sized numbers also. So here the total size of this one would be 3 plus 3, that is 6, 7, 8, 9, 10, and 11. So it will be 11 bits. And what will be the value? The first the bit which that is the value of A, that is which is 1, then B which is 0 0, C which is 1 0, and D which is 1 1 0, and the last one is 0 0 1. So 0 0 1. So this will be the concatenated value and its size will be 11. So here, so this is with respect to different sized operands which are present you're concatenating. Now I want to have say bit select, for example. So here we have open brace and a closed brace in between separated by the commas. We are taking the operand A, then we are concatenating it with the 0th bit of B, then we are concatenating this with the say bit at the first location. Here this is a bit at the 0th location of B, this is the bit at the first location of C. So here what happens is, you can observe, so A is just 1 bit, I'm not specifying anything over here. So it will be 1. Then B of 0. B of 0 is this part. That is the first 0. Then C of 1. C of 1 is this part. That is 0. So it is the other one. This is LS bit. This is LS bit, and this is the you move towards the MS bit. So at the first here, since only one bit is there, it is 1 bit. 0 indicates the LS bit, B of 0. And next one we have C of 1. That is, in this case, since it is just a 2 bit, this is the MS bit. So it will be 0 and this will be 1. And this is 3 bits long. This is three bits and it is binary. So this is the result what you'll be getting when you are concatenating using the concatenation operator. Now next one is the replication operator. So which is one of the special features in special operators in your Verilog. So in replication operator, what it does is the name itself tells that it has to replicate. That is, it has to produce some repetitive operation, to perform some repetitive action. So that is what it specifies. So here, what this does is it repetitive concatenation of the same number can be expressed using the replication operator. Now, here, for example, if I specify, if I just consider this, say I want y is equal to a comma a comma a comma say 100 times. I wanted it 100 times. So it is not feasible to write a 100 times, and it becomes difficult to keep track of how many times you have written it. So instead of doing it, what I can do is I can use the replication operator, which specifies that a has to be repeated say 100 times. A has to be repeated 100 times in the concatenation part. So that is what we can observe here, replication operator. So it is just this brace what is present. So here we have register A. So let us just check with respect to this one. So A, here we have specified the value. It is just logical, it is just bit 1. So here what it is specifying, it is specifying that you have to repeatedly concatenate A 4 times. You have to repeatedly concatenate A 4 times. So in one sequence only, it will be concatenating. So here, since A is 1, what happens is this Y will be concatenated and 4 ones will be present. And this is 4 bits in size. Now the similar operation can be clubbed with the other concatenation parameters. So here we have, for this part, we have A is repeated 4 times. A is repeated 4 times. So this, if you are using replication operator is the curly braces. It is within your concatenation operator. Okay. So A is repeated 4 times. So the first four, this thing will be related to A. Then next B is concatenated by itself 2 times, and thus this concatenation result is concatenated with this part. So here what we have 0 0 in B and 1 in A. So what it is specifying, A is, I'll just write the number, and B is 0 0. B is 0 0. So what is specifying? Is specifying A has to be repeated 4 times, and this has to be concatenated with B, which is repeated 2 times. So this is the overall result. So this is the concatenation part. So A has to be repeated 4 times. It is 1 1 1 1, since it is just 1 bit. And this one has to be repeated 2 times. So it is 0 0 first time and 0 0 second time. So this is your overall result, which will be stored in say Y. So similarly, we can perform it in this form. So if you're not specifying anything, it is just repeated only. It is only one time which will be coming over there. So this is your replication operator. So in next class, we'll be looking forward for conditional operator, and we'll be looking forward for one example.